Morning, welcome to the video. Here, today discussing about the rotating bodies and rolling bodies. Right? Discussing about the rotating bodies and rolling bodies. Now here we get the first of all small thing missing in the rotating rod. Moment of inertia, moment of inertia here, rotating rod can be rotated two ways. This is the rod, uniform rod, uniform rod. Then perpendicular axis is rotate omega angular velocity, omega angular velocity. This length of the rotating rod L, the mass of the rod capital M, and through this axis, perpendicular axis, these two axes, this axis rotating, this is rotating, right? Now, it can be seen that this one, but that I equal 1/12 ml square. This is the rotating rod. Other bodies already discussed earlier. Now rotating this one, end of the axis perpendicular to the rod, this axis, omega. This is also same. This is some different about here. Mass is same. Here, in this case, inertia is equal, moment of inertia equal 1/3 ml square. You remember that, this one, right? Every geometrical figures at rotating, they have radius of gyration also. I will later discuss in summary video how to calculate the radius of gyration, all of the moment of inertia in the rotating bodies, geometrical shape, right? Now here today discussing about the rotating work done. We know that the work done is the force into displacement. Normal linear condition. The translation motion. Here this is the M mass mg, right? Mg Newton with the applied force F. This is somewhere at the time t. This is displaced to this sphere here, displaced to here, right? Position change. Now displacement is x. In work done is given if W equal force into displacement. F force into displacement. In rotating case, what's happening? In rotating work done also having rotating bodies. This is calculated normally like this. We take the disk. We take the disk, right? Rotating disk. We shape this. This. Right? This disk rotating about perpendicular to the plane, this axis, omega. It will rotate initially, we have to given some torque. With that torque, it can be rotated. Actually, motor case also same time. Initially, they given the torque by the electrical devices using. Here also, any mechanical device also using, you have to use the torque. Torque we say this one. Torque. Torque is the torque, given torque. Torque is the given torque. Actually, in the torque apply, already I am considering here torque and moment some difference have. Torque having every time having the acceleration also, angular acceleration. Angular acceleration we take alpha, right? This statement angular acceleration take alpha. And other thing, it has some what we call uh, displacement. This is initial point. Initial point here. After time t, this come to P1 to P3. P1 to P3. Displace theta angle. Angular displacement theta. Theta is angle. Angular displacement. Theta angle rotate. Right. Theta angle rotate. Then angular is the condition. Rotating work done. Work done are rotating. Na? Work done rotating equal tau into theta. Instead of the tau, linear condition using force. Instead of the force, here this condition using tau. Tau. Tau take plus. Take this condition. Right. W equal tau theta. Right. This work done to be time taken t divided by time t. What is happening this one? W R O T rotate. W rotate equal omega over theta over t. What is the theta over t? Rate of change of angular displacement. Rate of change of angular displacement is the omega, angular velocity, equal tau into omega. Here also this can using t, W over t. Work done per unit time. Work done per unit time is the power. Power. This condition have rotating power, PT, PR, PR, PR. Rotating power is omega into P. Omega, tau into omega. Tau into omega. Tau omega. Rotating power is equal to omega. Right? Rotating power to omega. Rotating work done to theta. Torque into angular displacement. Here, torque into angular velocity. Right? Right. You may consider in a little time, 2 minutes time, you require this thing. If you want to write down, you can write down also. In the rotating body, here this case, another condition, another thing I am taking to here. This is a rotating wheel, rotating about initially applying torque, torque, apply. Acceleration alpha, right? Acceleration, angular acceleration is alpha. The moment of inertia of the this disk, we say I. I about this axis, right? About this axis I, right? In some relationship can have I, tau and alpha, another relationship. This condition is normally saying rotating disk or rotating body, apply the torque alpha, apply the torque tau, and it happens given angular acceleration alpha. Some relationship have tau and I alpha. This relationship equation is tau equal I alpha. I alpha. But that tau equal I alpha. Tau equal I alpha. This is another equation. What's the relationship? Tau equal all the time I alpha. I is the moment of inertia in the rotating body. Alpha is the angular acceleration. Tau is the applied torque. Right. If we are saying about the tau, all the time having angular acceleration also. If the torque vanish, angular acceleration also sometimes vanish. It can be then rotate uniform uniform angular velocity. Then torque hidden, then angular acceleration also zero. Then in this case, what's happened? Tau equal I alpha, valid or not? In this case, not valid. Uniform condition. Right. Now, again, we come into the rolling body. Rolling body. Rolling body. Total energy. Right? Rolling body, total energy. How to calculate? First of all, we consider the energy condition. Energy, we know that. Energy behave with what that? Potential energy and kinetic energy. In the traveling body, having the kinetic energy. In the body under gravity, placed on one place, it exists with energy, potential energy, right? Right? This is the mechanical energy form of the mechanical energy. Mechanical energy form of one is the MGA. MGA is the potential energy. Other one is the half mv square. Half mv square with the motion body. We say this one. M mass travel with v velocity. V velocity. Moving it v velocity. V velocity. Then it giving kinetic energy. Kinetic energy, right? In the translation motion equal half mv square. Half mv square. Half mv square. This can be applied to the rotating bodies. We say somebody rotate, right? Somebody rotates, right? This path rotate with the linear velocity v. Mass m. Mass m. Mass m. Mg. Right. Now we know that angular velocity omega. Angular velocity omega. Right. Omega and radius are some have relationship. Earlier we discussing all those things. V equal omega r. V equal that omega r. Then we know that omega r we are taking. What is that? V equal omega r. We substitute to here. V value, this one substitute to here. Then kinetic energy rotating. Kinetic rotating equal half m into V equal omega r. Omega r substitute here V squared, omega squared, r squared. R squared. Kinetic energy rotating equal half m r squared into omega squared. Omega squared. What is the half m squared? Disk. We may consider this a disk. Perpendicular to this axis, what's that? Moment of inertia, half m r squared. Geometrical figures earlier videos we discussed in. You see the video, you can see half mr squared is the I, right? Then it will give in kinetic energy rotating equal I omega square, I omega square, half I omega square, half I omega square, right? mr square is I, half I omega square, right? Now here we say what is happened? Mass here, mass and velocity here in the linear condition, right? Translation noted. In the rotating condition, moment of inertia, instead of the mass here using, but the I, velocity replaced by the omega, angular velocity, right? Kinetically rotating half of I omega square, right? Now you will see here all those things, right? Now before all those things, little bit time. Now we are coming to the rolling body total energy. What is the rolling body total energy? It can be expressed as the rotating energy and linear translation energy. There are two ways. Kinetic energy, two types. One is the rotating, one is the linearity condition. Their total energy, they both head of the energy condition. Right. Now we consider the wheel roll in a horizontal plane. Wheel roll in the horizontal plane. Right? V velocity is the rolling body. Right? Rolling body, rolling wheel. Right? Rolling wheel. Rolling wheel. Omega angular velocity rolling. It will come to another place, this one. After rolling, it will come, travel like this. This path is like this. Center of here. Center line has the velocity. Center line has the velocity. Linear velocity V. Right. This is the omega. Is traveling further like that. Right. This is the total energy. Energy total. Energy total is equal all the time. And that energy total is this is the mass m. Mass m. Mass m. Mass m. Kinetic energy for the linear condition. Half m v square plus the kinetic energy have the rotating condition. Rotating condition, we know that this axis perpendicular to this axis, perpendicular to the board and the plane. Board plane perpendicular to the center. Have some axis. This axis to having all the time moment of inertia. I. This is the now kinetic energy I omega square. I omega square. This is the equation of the rolling body total energy. Right? Kinetic energy, two types have. One is the linear type, half m square. Other is the half I omega square. There are two types. Right? Total energy half m square plus half I omega square. Right? Little time given, you will, if you are getting some notes also, sometimes you can get the note. Right. Now another one I'm explaining here. Cylinder rolling on the inclined plane with inclined plane. Cylinder rolling on the inclined plane. Now here we taking solid cylinder. Now we are taking solid cylinder, rolled in the inclined plane. Inclined plane. There's no friction also. Inclined plane is considered with the assumption. This is the inclined plane, right? Angle, theta angle, inclined plane. This is the cylinder cross-sectional area, like this cylinder, cross-sectional area like this. Radius R. This distance, normally H distance about the flow. It's a flow condition about the flow here. Right. It will come to here. What is the velocity? If we need to find out the velocity of the inclined plane downward position, with the end position in the here. End position of the here, we draw the diagram like this, velocity V. Distribution velocity V. This is coming, rotating, rolling and coming to here, right? Initial velocity is equal 0, u equals 0. Initial velocity 0. U equals 0, V O V. These are this perpendicular to here, this axis, right? And moment of inertia I. Right? You take moment of inertia I. Due to the rotating, due to the rolling, it having omega, but that angular velocity, right? It will come to here, right? Angular velocity. Initially, this start from rest. It will come to here, some values have, velocity values have, right? In the rest condition, total energy, what the total energy of at A? Is the A point, is the B point. At A, energy total. What that? Kinetic energy 0, the rest position. Rotating kinetic energy also 0. But have only, what that? This A, mass M. But it having, due to this portion above the ground level, kinetic, not kinetic energy, potential energy having. Total energy, MGA, potential energy. Right? At B position, what having? Kinetic energy and rotating kinetic energy and linear kinetic energy, both having. At B, E, T, B equal half I M square, half M V square plus half I omega square. In this one, we earlier discussed about that. V is the velocity at the end point. Omega is the rolling body or rolling cylinder. But then, rolling cylinder, angular velocity, right? Then ATB equal this one. This energy is the equal, right? Conservation of energy law. Conservation of energy law said that the energy equal at B. Therefore, we can say equation, two equation, but the two equation. This one, but that ETA equal ETB. Therefore, we can say that MGA, ETA is MGA equal This one, half m v square plus half I omega square. Omega square. Right. This equation using, we can calculate the v. If we need to take the v with the radius, you can see that v equal omega, v equal omega r, v equal omega r, right? V equal omega r. We know that omega is equal v over r, right? Now we can say that equation coming mg8 equal half mv square plus half I is equal, what is that? I is equal half mv, moment of inertia I, to this axis. I is equal mr square, half mr square. Now both in we substitute here for that. Half I equal mr square, mr square over 2 into v equal omega is equal v over v square over r square. R square cancel. Here equation comes with m and v, m cancelling. Then we get it the equation. This equation using we can calculate the v value. V value can calculate, right? Actually, this one leads to the so many sums, problems. So many problems given the examination like this. Right? We can calculate v in this equation using. Right? But that cancel it. Right? V and other you can subject the v, you can get in the all those things. Right. Now later again I condition this circular motion, start from the circular motion, rotational motion, inertia, rolling bodies, all those things. Summary discussing next video. Next video also I am discussing about the drum wing or wind drum. Normally wind drum using the normally ships using the prose handling. Prose handling. Now finish the video. Thank you very much.